Hello, I work in Ericsson, based in Italy. I'm the strategic head of product line Optical. This presentation will run for around 10 to 15 minutes. I will cover the advances in RAN technology, their impact on networks, and in particular, how they are driving requirements necessitating advances in optical technology. The presentation has 4 sections and will close with a brief summary. Firstly, RAN evolution. Here I have summarized how the RAN or radio access network has advanced over the last 40 years, which roughly matches my involvement within the industry. It's clear that as the RAN has evolved, new technologies have arrived to meet this evolution. From PDH to SDH, ATM and IP, efficiencies in packet processing have been necessary. The infrastructure has evolved, from copper, microwave connector cell site through to optical innovations and new solutions. Interesting also to note that if you look at the typical capacity required at those cell sites and the devices connected to them, there's quite a dramatic change from a 2 megabit backhaul and voice services of several kilobits all the way through to today with typically 10 gigabits or multiple 10 gigs connecting the remote cell site and voice and data requirements of the mobile unit capacity greater than 1 gigabit. The impact of this technology evolution is captured in the next 2 slides, which here you can see that global mobile traffic data growth has grown in the last 5 years. Here I would say from around about 2 exabytes of mobile traffic worldwide from our calculations, we see that by the end of this year there'll be around about 60 exabytes of traffic per year, and that's showing growth year on year of around 46%, and in the last quarter 13% growth. So clearly smartphone advances and the services such as video are fueling this growth. By 2026, Ericsson predicts that 5G will be deployed globally, with approximately 3.5 billion 5G subscriptions, representing around 40% of all mobile subscriptions. At the end of 2020, over 1 billion people, or 15% of the world's population, were living in areas with 5G coverage. Interesting that over the 40 years, the early handsets, as mentioned, carrying a few hundred kilobits per month, here we can now see that on average 10 gigabits is the typical smartphone usage per month. So, as RAN has evolved in terms of speed and performance, so too has the network and its architecture. The 2 main deployment architectures are when the baseband processing, or layer 1 processing, is distributed to each antenna site. This is known as distributed RAN. The other main deployment architecture is where the baseband processing, or RAN compute, is centralized and serves many antenna sites. Both of these techniques are in operation today. Some techniques favored to a greater extent by some operators using both techniques, and some operators with a highly strong preference for a centralized architecture for a variety of reasons. And obviously the upcoming cloud RAN deployments will need to support both distributed and centralized RAN architectures. In the next section, I will cover in more detail the requirements emanating from the different architectures and identify areas that operators need to be aware of when deciding on an architecture and the optical solution to support it. So this is a summary of the bandwidth and latency requirements on transport for the various interfaces in the different 5G RAN architectures. Depending on how much new NR spectrum is used and the number of sites aggregated, the requirements will vary, typically within the range indicated in this picture. One of the architectures I'm highlighting here is CRAN, or centralized RAN, whereby the basebands or RAN compute devices are centralized in a location remote from the antenna sites. Typically, this will be at a distance of up to 15 to 20 kilometers. This architecture is of particular interest to operators who are keen to improve the performance in a particular area of their network, or if that operator has a particularly restricted space at the antenna site, which is to limit the amount of equipment he's putting at that particular site. And also it helps operators who are keen to lower their OPEX by reducing the amount of complex equipment out of the remote site, centralizing that in a in one location. The 15 to 20 kilometer distance is dictated by RAN protocol timing constraints. For multiple 10 gig, CPRI and eCPRI, this is not a problem. As the newer radio technology starts to demand multiple 25 gig, 50 and 100 gig, along with tighter synchronization requirements, then this starts to stress the abilities of optical transceivers. So while clearly a CRAN architecture brings performance benefits, the location of the baseband hotel is restricted to some extent by the optical performance available at that particular time. Now I'd just like to show an analyst slide showing the type of transceivers that are dominating today in the fronthaul and backhaul arenas, and the analyst view sharing the future trends that they see. Clearly today 100 gig for backhaul is the dominant technology, and up to now 10 gig has been the dominant technology in the fronthaul arena. But we're now starting the ramp up, I would say, for the era of 25 gig in the fronthaul. But also interesting to note that tunability seems to be becoming foreseen to be more prevalent along with 25 gig, mainly driven by the fact that tunability at 25 gig is going to be more cost competitive than it was available in 10 gig, and the fact that operators are now very keen to reduce OPEX, so simplifying the installations and tunability gives them that possibility. Expect 100 gig to continue to grow from the backhaul aggregation, probably until around 2023, where I would expect 400 gig, which is shown here, starts to appear. I guess the question to ask is, will the transition to 50 gig electrical SerDes happen also within this time frame? This final section looks at the future technology choices and highlights the differences between telco and datacom. So optical requirements from the datacom world are different to those from the telecom world. Clearly, large datacom volumes drive early adoption of optical solutions for datacom requirements. And we see that there's roughly an 18-month lag from the electrical SerDes advances being adopted eventually then in the telecom optical solutions. I really need to underline at this point that optical solutions are very different in the telecom world compared to datacom. So here I'm showing the fact that solutions need to operate in much harsher conditions. They need to have a very high availability. We're talking of thousands of cell sites in an operator's network. A transceiver failing with a common fault is a massive impact on an operator having to visit individual cell sites in those kind of quantities to replace an optical device. And obviously, as RAN technology speeds have increased dramatically, that also comes with the need for far higher quality of sync solutions. So the transceivers need to meet those sync requirements. So if I zoom in on the hot topic in my world of telecom, having worked over the last few years delivering solutions at 10 gig in CRAN, I'm now challenged to match a 10 gig optical performance at 25 gig, which is not easy. And I'm challenged from a price and optical performance perspective. And not only that, operators, as mentioned, are really keen to take advantage of any OPEX reductions associated with the introduction of 25 gig, such as tunability. And not only that, as RAN evolves, we need to work with optical developers to find the right solutions for 50 gig. And solutions here I'm looking at and showing in this graph, potentially O-band is seen as a potential good solution here, offering good reach performance when it comes to handling dispersion, but maybe not necessarily if you're in a situation with fiber that is of a challenged quality. And so it may be that both an O-band and C-band solution for 25, 50 gig and beyond, both of those solutions may need to play a role. So in summary, I would say I'd like to underline that optics are a key component of radio access networks. They need to be specified to meet stringent RAN requirements: reliability, power, temperature, and latency. A range of solutions are required to meet the various evolving RAN architectures and operator requirements. Thank you.